This lesson is going to start on section 5 out of the book, which is the first look that we have at eigenvectors and eigenvalues. So just to set up what eigenvectors and eigenvalues are, we're going to go harken back to matrix multiplication. When we talk about eigenvectors and eigenvalues, we talk about eigenvectors and eigenvalues for a matrix. So imagine what happens when you multiply a matrix. So if we have this matrix and we can plot the vectors v and av for any vector. So in other words, if our vector v is 1, 0, we can plot 1, 0. Multiply it out, so av becomes minus 5, 8. Then we can plot out the vector minus 5, 8. And you can do that for any vector. So if you start with 1, 1, if that's your vector v, you can multiply it out and you can get av, which is minus 9, 15, which points over that way. Again, minus 2, 1. You can just do this for any vector at all that you want. You can plot out both the vector you start with and the vector you get after you multiply. But sometimes something special happens with these vectors. Take the vector 1, minus 2. Multiply it out by your matrix, and you get 3, negative 6. Notice what this is. You start out with a vector. You end up with a vector that is just a scale of it, that's overlaying it. So all the other vectors pointed in different directions. This one points in the same direction. So when you multiply by the vector 1, minus 2 by that matrix, all you do is you scale your vector. It could be positive, it could be negative, but you're just scaling your vector. It's still pointing in the same direction or in the negative of that direction. This is called an eigenvector. When you have a vector that when you multiply by a matrix just scales it, we call it an eigenvector. And this time you start out with the vector 1, negative 2, you end up with 3, negative 6. So it becomes 3 times as long. That's our eigenvalue. So our vector is an eigenvector. The number 3 is called the eigenvector because it turns that vector into 3 times its size. When you have matrices, this is a very special property, and there are all kinds of physical applications where you look for these vectors, these eigenvectors. This is where special things happen with matrix multiplication. So the formal definition is that if you have an n by n matrix and you have a vector, it's called an eigenvector if AV, in other words, multiplying that vector by the matrix, is equal to lambda v, is the same thing as multiplying it by a number. That vector is called the eigenvector. The scalar, the number in there, the lambda, is called the eigenvalue. So for instance, for this matrix, you multiply this out, what do we get? Well, you get negative 4 plus 12 minus 5. You get minus 9 plus 14 minus 11. You get minus 8 plus 16 minus 11. When we add these things all up, we get 3. That's 3 minus 9, so minus 6. This is 8 minus 11, minus 3. So notice again, this is negative 1 times the vector we started with. So here we have an eigenvector is negative 1, 2, and 1. And the associated eigenvalue is negative 1. So here's an example. I've given you a matrix and I've told you what 2 of the eigenvalues are for it. Now note that there's more than one eigenvalue. You'll normally see that a matrix will normally have multiple eigenvalues and multiple eigenvectors. So in this case, I've given you 2 eigenvalues and asked you to find the eigenvectors. So let's take the first one, negative 1. What does this mean? This means that our matrix 1, 6, 1, 2 times some vector x1, x2 is equal to the negative of that vector, negative x1, negative x2. So now let's write these out as equations. It gives us x1 plus x2 equals negative x1, and it gives us 6x1 plus 2x2 is equal to negative x2. Rewrite these a little bit by bringing the variable over. We get 2x1 plus x2 equals 0, and we get 6x1 plus 3x2 equals 0. Now, if you take a look at these equations, you're going to note that one is a multiple of another. So it's going to give us a pretty easy way of finding this vector. Take that first equation. We have 2x1 plus x2 equals 0. So we have x2 is equal to negative 2x1. Now we can take whatever we want for x1 and x2. We can say let x1 equal 1. Then x2 is equal to negative 2. So our vector x1, x2 is equal to 1, negative 2. There is an eigenvector. Now, as we're going to see, there's infinitely many eigenvectors for this eigenvalue, but this gives you an eigenvector for that eigenvalue. And we can do the same thing with the second one. So with our second eigenvalue, we multiply it by x1, x2, we get 4x1 and 4x2. Again, the equations are x1 plus x2 is equal to 4x1, and 6x1 plus 2x2 is 4x2. Rewrite them a little bit. Negative 3x1 plus x2 is 0, and 6x1 minus 2x2 equals 0. Note again, one of these equations is a multiple of the other. This is something that's going to be important. So we can take that first equation again, and we get that x2 is equal to 3 times x1. So we can say let x1 equal 1, then x2 equals 3. So we have that x1, x2 is equal to 1, 3. And there is an eigenvalue for eigenvector for the eigenvalue of 4. So finding eigenvalues and eigenvectors. So how do we find them? This is a little bit of a theoretical step for trying to find them. We are looking for a solution for ax equals lambda x. So in other words, we have our matrix. We're saying what vectors can we multiply where that is just equal to a scalar times the vector we started with. So for some vector x and some scalar lambda. So we've got a couple of unknowns in here. When you're trying to find eigenvalues and eigenvectors, the first step is to find your eigenvalues. So in the last problem, I gave you the eigenvalues. Now I'm going to say, how did we get those? How did I get those? Well, let's just do a little bit of matrix manipulation. So we are looking to try solve ax equals lambda x. One thing that we know is that lambda x, we can stick the identity matrix in there, and we get the same thing, because the identity matrix times our vector is just the vector. Now that's using that x is equal to the identity matrix times x, where x is our vector. Okay. So the next step, take that stuff on the right-hand side and bring it over to the left. And you get this, ax minus lambda I times x is equal to 0. Well, note that you have an x in here both sides, so you can, using the properties of matrix vector multiplication, you can gather up those terms, and then you get this. A minus lambda in times x equals 0. Okay, so note what this is. This is a matrix times some vector equals 0. And this equation is an important equation that we are going to use to find our eigenvalues. So keep this in mind. So to solve this, we have to solve that equation. Now remember that x equals 0, the 0 vector, we don't consider that an eigenvector, okay? So we're looking for things other than x equals 0, things other than the 0 vector that will solve this equation. So this means that that equation will have an infinite number of solutions. Because remember, there's no such thing as a single solution. It's either you have no solutions or you have an infinite number of solutions, okay, for this type of equation. Well, when does this have an infinite number of solutions? It will have an infinite number of solutions exactly when that is not invertible. If it were invertible, it would have a single solution. So that means it's not invertible. What does it mean when it's not invertible? Well, remember the determinant. The determinant is equal to 0 when it's not invertible. So in other words, you are looking for lambdas where a minus I times lambda has a determinant of 0. This is the way that we are going to find our eigenvalues, using this fact that the determinant of this a minus I times lambda is equal to 0 to find the eigenvalues. We'll get into that a little bit more, but here we're going to start with this theorem, that the eigenvalues of a triangular matrix are the entries on its main diagonal. This is an easy one. So if you have a matrix, say for instance, I just make this up, 3, 2, 1, 0, 1, 4, 0, 0, 2. That is a triangular matrix. The eigenvalues for that are, the first eigenvalue is 3, the second eigenvalue is 1, and the third eigenvalue is 2. Why is that? Well, take a look at what we just saw a little bit while ago. We are looking for where the determinant of the matrix minus lambda times I is equal to 0. So what is our matrix minus lambda times I for this matrix A? What's this equal to? This is equal to 3 minus lambda, then zeros, 2 and 1 minus lambda, and 2 minus lambda. That is the matrix A minus lambda I. What's the determinant of a triangular matrix? The determinant of this, the determinant of A minus lambda I, you just multiply down the diagonal. 3 minus lambda, 1 minus lambda, 2 minus lambda. What makes that equal to 0? Well, that's equal to 0 exactly when lambda equals 3, lambda equals 1, or lambda equals 2. Exactly the responses we have there. So the eigenvalues of a triangular matrix are very easy to find. You just read off the numbers down the diagonal. So for example, find the eigenvalues and eigenvectors of this. Well, the eigenvalues are easy to find. Lambda 1 is 1, lambda 2 is 2, and lambda 3 is negative 1. Why is that? Using theorem 1, we have a diagonal matrix. So we're going to start with the first one. Lambda 1 equals 1. So we are looking for vectors where 1, 0, 0, where the matrix times a vector, x1, x2, x3, is equal to 1 times the vector, so is equal to itself. And let's write this out as equations. It gives us x1 minus x2 equals x1, 2x2 minus x3 is x2, and x3 equals x3. Or write it again as, well, the x1s disappear, so you get negative x2 equals 0. You get x2 minus x3 equals 0. And we get, for the last one, 0 equals 0. What does this tell us? This means that x2 equals 0 from that first one. It tells us that x3 equals 0, and it tells us that x1 is a free variable. You can set it to whatever you want. So the eigenvector is equal to 1, 0, 0. There is an eigenvector. And take this and multiply it by the matrix, and you'll see you come back out with 1, 0, 0. That gives us that eigenvalue. Okay, so now take the next one. With that matrix, our second eigenvector is 2. So again, writing out the equations, we get x1 minus x2 is equal to 2x1. We will get 2x2 minus x3 is 2x2. And we will get minus x3 is equal to 2x3. And again, we can solve these out. Rewrite them. We get negative x1 minus x2 is 0. We get negative x3 is 0. And we get, for the last one, negative 3x3 equals 0. So what does this tell us? Well, this tells us that x3 is equal to 0. And then we just have the condition that x1 and x2, we can say let x1 equal 1, then x2 equals negative 1. So my eigenvector is equal to 1, negative 1, 0. And there's an eigenvector for that eigenvalue. Now my last one was lambda 3 equals negative 1. You can try this on your own. Try to find an eigenvector for that eigenvalue. Okay, now theorem 2 talks about these eigenvectors. And one of the properties of eigenvectors, one of the important properties, is that your eigenvectors are actually going to be linearly independent. Now, when I talk about the set of eigenvectors, I say if you have your eigenvalues, take one eigenvector that corresponds to each of those eigenvalues. As we've seen, there's infinitely many because they're multiples of each other, but take one eigenvector that corresponds to each of the eigenvalues. Then that set of vectors is linearly independent. This is actually an important property of eigenvalues, eigenvectors. If you have this set of eigenvectors, they are linearly independent of each other. And why is that? Okay, so to show it's true, we are going to go through some of the properties that we've seen before about linear independence and dependence. We are going to show this by saying, well, let's assume we're wrong. Let's assume that these vectors are linearly dependent. Then what happens? And we're going to show something goes wrong. So if our set of eigenvectors are linearly dependent, that means that there's somewhere along here in this set, when you're building up the set, that you suddenly get linear dependence. So V1 is linearly independent, a single vector. V1 and V2, then you start with V1, V2, V3, then V1, V2, V3, V4, and so on. So you're building up one vector at a time. At some point when you're doing this, you end up with a set that is linearly dependent. where everything smaller than it is linearly independent. So take that set. So we're saying the set V1 to Vp plus 1 is linearly dependent, but everything smaller than it is linearly independent. So V1 through Vp is linearly independent. You throw on the P1 vector, it becomes linearly dependent. What does that mean? That means you can combine those first P vectors to get the P plus first vector. That's one of the properties we saw about linear dependence. So we have that equation. We'll call it the star equation. Just take that equation, multiply everything in it by that eigenvalue, lambda p plus 1. So we're just sticking the p plus 1 in on all the terms. Okay? This is the double star equation. We're going to use this again. Okay? So we've just taken a linear dependence and multiplied every term by something. It's still equal. So go back to that first one that says they're linearly dependent. Well, we can multiply everything through there by A, our matrix A. So we stick our matrix A in every term. There's nothing wrong with that. We're just multiplying everything by the matrix A. But remember, A times V1, that's our eigenvector. So we can replace that with lambda 1 times V1. A times Vp is lambda p times Vp because they're eigenvectors and eigenvalues. All the way to A times V plus 1 is equal to lambda p plus 1 times Vp plus 1. So now that equation, take that and subtract that double starred equation from it. What do you get? You end up with this. If you go back and see the double star equation, you'll see the thing on the right-hand side is the exact same. The stuff on the left-hand side is slightly different. What do you get when you subtract them? You get all of this is equal to 0. In fact, a little too far, you get that this equation is equal to 0. What is this equation? This is something times V1 plus something times V2 plus all the way up to something times Vp is 0. What does this mean? This means you have a way of combining those first p vectors that's linearly dependent. But we start off by saying that that can't happen. So we've created a contradiction. So this shows that those vectors are linearly dependent, and that's a contradiction. So in other words, we can never have any linear dependence in our set of eigenvectors. It can never happen. Our eigenvectors are always linearly independent. This is a property we're going to use again in the next few classes. So definition. We've talked about eigenvectors and we've used this equation. A minus lambda 0 times in times x equals 0. Notice that this is kind of familiar. What do we have? We have a matrix times a vector equals 0. A matrix times a vector equals 0. When you solve for that, what are you solving? That's a null space. Eigenvectors give you null spaces. If you know how to solve a null space, which we've been doing for the last few lectures, you can find your eigenspaces. What do I mean by an eigenspace? Well, remember when we found the eigenvectors, we found that we had a free variable in there. So that means we had a vector space. Well, that is called the eigenspace. A vector space that's based on your eigenvectors is an eigenspace. That eigenspace is just the null space of not your matrix, but your matrix minus your eigenvector, or eigenvalue, times the identity matrix. So for example, we want to find the eigenvalues and eigenvectors of this matrix. And in fact, I've given an eigenvalue. So we're just going to find the eigenspace for that eigenvalue. So to find that, we first find our matrix A minus lambda I, or in this case, A minus 4I. What does this give us? This gives 6 minus 4 for there. It gives 5 minus 4 for there. And it gives 7 minus 4 for the last one on the diagonal. So it's equal to 2, 2, 2, 1, 1, 1, 3, 3, 3. Notice what we're getting here. You can already see that you're getting linear dependence in all your rows and columns. So now what we're doing is we are looking for the null space of this vector. So that thing, we have to find the null space. And this is something we've done before. So how do we do it? We row reduce. And I'm going to do row 1 minus row 2 is the new row 2. And to save time, I'm going to do row 1 minus row 3 is the new row 3. What are you going to get? 2 rows of zeros. So now what do we have? This gives us basically the equation 2x1 plus x2 plus 3x3 equals 0. Or when we rewrite this, we will get x1 is equal to negative 1/2 x2 minus 3 over 2 x3. x2 equals x2 and x3 equals x3. Those are my free variables. So x2 and x3 are my free variables. What does this give me? This tells me that my space, x1, x2, and x3, is equal to x2 times something plus x3 times something. What are those things? Negative 1/2, 1, 0, negative 3 over 2, 0, and 1. This is just solving for null space that we've done all kinds of. So this gives me the description of my eigenspace. So my eigenspace has a basis of negative 1/2, 1, 0, and negative 3 over 2, 0, and 1. The same way that we find a basis for our null spaces. So there's an introduction to eigenvalues and eigenvectors. We're going to be next looking at these in a little bit more detail.